Hey, so today we're going to be going over a boundary condition problem. Um, this is from homework 6.14. We have a large block of material with permeability 5 mu naught is found to be tilted at an angle of 53 degrees from the x-axis as shown in the figure. The magnetic field above the surface is in air, and it's given uh, H the magnetic field of H1 with the components 2, -4, 0 in Cartesian coordinates. We know that there's a surface current of a magnitude 3 in the negative y direction at amps per meter is its units, and this is surface current is observed at the boundary. So what is the H field just below the surface? So here we have a boundary with we need to find the H field below the surface, and we know that above the surface in air we have a magnetic field of H1, which is given. So we know H1. We need to find H2, and here we have our surface, our boundary. This is material one, material two. So to start off this problem, we should understand our uh, our equations and what they're saying. So we know that the H field, this is the our magnetic field intensity. We know that the B field is another form of the magnetic field, but it's the magnetic induction. So these are both vectors, and we can use their relationship to find the H field of the boundary below. So, what is boundary conditions? What's the benefit of studying them? So, studying boundary conditions allows us to understand how electromagnetic waves affect objects, and we can use this to determine what the electric field or magnetic field inside the object is and how it's reacting to the electromagnetic wave. So, understanding this and using the following relationships, we can find each two. So, we're going to use the relationship between B and H, which is B equals mu H, and mu is the magnetic permeability of a material. So this is essentially how much magnetic field can be stored inside the material. So mu equals mu naught mu r. So we know that there's uh, two boundaries with two different materials, one in air and one with 5, which is given as 5 mu naught. Uh, so to start this problem, uh, we're going to solve it using the algebraic method instead of the matrix determinant method. So first we know that every 3D object has one normal component and two tangential components, T1 hat and T2. So this is true for all 3D objects, and we're going to use this to find the two tangential components and the normal component. And using the relationships given, we're going to find H2. So first, um, first relationship is B1n, is B2n. So this is derived from Maxwell's equations. We know that the normal components of the magnetic field are always continuous to each other, unchanged or equal to one another. but we need to take into account their magnetic permeability of each material. And we're also going to be using N2 cross product of H1T vector, H1T vector minus H2T vector. And if we do the cross product of these two, we are able to derive the surface current density. So we know that free charges stay on the surface of a conductor. We can also use this to determine the free current on the surface, or on the boundary. So we're going to use these two equations to find our normal and two tangential components. So first we need to find our normal and tangential, our n hat and t hat. So n hat, our first n hat is going to be normal to the surface, and the surface of the boundary, we know that it's tilted at 53 degrees. So we need to break this normal component into its vector components. We need to break this vector up. So we know this is N2. And to find what N2 is, we're going to use trigonometry. So we know that this is right here is 53 degrees. We know if this is the right triangle, this is going to be, I believe, 37 degrees. It's right here. So this is right here is going to be 37 degrees. So this is true, and we draw our axis here. We know that this angle right here using trig is also 53 degrees. So if we know that, now to break this vector up, we know that this is our cosine in the z direction, and this is our sine is going in the negative x direction. So now we write n hat and 2 hat equals cosine 53 in the z direction minus sine 53 in the x direction. And if we put this in vector notation, this equals negative 0.8, 0, 0.6. So remember, this is in Cartesian coordinates. And now we're going to find our tangent, or t hat, our first t hat. This is going to be, this is our t hat. Let me also make note that the surface current on the boundary, the surface current is in the negative y direction with a magnitude of 3. So where is negative y? We know that our axis is x and z. So y, if we do cross product of z and x, we know that y is going to be going into the page. Z cross x cross z is negative y is up, so positive y is into the page. So we know that the surface current is only in the negative y direction. So let's go back to our tangential component. You know that this is going to be, to break this up into a vector, This is our cosine is going to be in the x, and our sine is going to be going in the z direction. So sine 53. Oh, I messed this up. Cosine is our x. Sine 53 is our z. So our tangent is our t hat. If we put this in vector notation, it's going to be 0 0.6, 0, 0 0.8. So now we have our n hat, our t hat. Let's solve for, before we go into that, let's solve for our B2n. Uh, our B1n, we have our relationship of B and H, so we can find our B1n, and then we can relate that to B2n using our permeability that is given. So B1n equals mu naught, because it's an air, it's only one H1n. And what is H1n? What is the normal component of the H field in the first boundary? H1 in the first material. H1n equals our H1 vector dot product with our normal, which we just found. H1 is given, so this is 2, -4, 0, dot product with our n, -0 0.8, 0, 0 0.6. And if we multiply these, do the dot product, and add each of xyz's up, this equals to -1.6. So you would just multiply these out, and then add up, sum those up, and you get -1.6. Okay, so now to find B2n, 5 mu naught H2n, based on our relationship. So we can combine these. B1n equals mu naught -1.6 equals B2n mu naught -1.6, 5 mu naught H2n H2n. Solve algebraically, you get -0.32. Okay, so now we found H2n, which is the normal of our H2 field, which we're trying to find. So we found our, like we stated, every 3D object has a normal and two tangential components. So now let's find our first H1t. H1t equals, just like how we solved for H1n, or H1 times t hat are dotted together. So that's the vector notation of our H field. -2, -4, 0, dot product 0.6, 0, 0.8. And multiply these out, be 1.2 plus 0 plus 0. So H1T equals 1.2. Okay, so we have B1N, H1T. So to find, we're going to use the equation for our surface current to find the H2Y and H2T. These are the tangential components needed to solve for H2 in Cartesian coordinates. So using equation again, it was N2 N hat 2 cross H1T minus H2T equals our surface current. So looking at our problem, our first one, our first tangential component, if we do, so let's solve for the one in the y direction. We know that n hat n, so we're solving for n cross y. If we do, which is y, n cross y, it's going to be negative t hat. So using this equation, but the thing that you should know, we need to know, is that our surface current was only going in the negative y direction, not in the tangential direction. So there's actually no surface current going um, in this direction. If we did we did our cross product of n2 cross y, we know that's negative t h1y. Oh, h1y is given. That is negative 4 minus h2y. And we know that there's zero current in the tangential direction. Cross these out. And we're able to solve for h2y equals negative 4. Now let's do the other tangential component. We're going to do n cross t. And if we do n cross t, like we said, we do the cross product between these two, get in the y direction. So we're going to use this equation again. N cross tangent h1t, h2t, JST. And so we know that the cross product of these two is the y. So we know that there is a surface current in the y direction. And we found our H1T already. This is 1.2 minus H2T equals negative 3y. These cancel out. H2T. Solved algebraically, we know H2T equals to 4.2. So now we found our two tangential components and our normal component. So now we use this following equation to turn to change this vector back into Cartesian, and it's going to solve for H2 vector, which we're trying to find. So following equation puts it back into XYZ, H2n dot product of n hat plus H2y dot product with the y hat plus H2t times t hat. So we found all these values, we just plug them in. H2n was negative 0.32. Our n hat was negative 0.8, 0.6 plus H2y was negative 4, 0, and there was only one y hat, and it was a magnitude of 1. H2t was given 4.2, 0.6, 0, 0.8. This becomes, you multiply this out, 0.256, 0, negative 0.192. So we have to add all these vectors up, and this is going to sum up to our final H2 vector. 0, negative 4, 0, plus 2.52, 0. So remember, scalar times a vector is the vector, and you can add these vectors up together. And this is going to be H2 equals, if you add all these, this is X, Y, Z, X, Y, Z, X, Y, Z. This is going to be 2.776, 4, 3. And you can simplify to as many stick figures as you want, but this is the correct answer for this problem. We found H2 vector, and this was solved again using the equations of our Maxwell's equations and solving for each component algebraically, in contrast to the matrix determinant method. But yeah, that is our boundary condition problem.